Welcome back to Science with Sleepy, where curiosity drifts like starlight, and tonight's journey stretches across 2 full hours, because the universe never runs out of wonders. Imagine the lights dimmed low, a gentle hum of ambient sound behind my voice, and your favorite blanket pulled close as we drift into the deepest questions about worlds that wander alone. Picture this, a planet floating through space with no star to call home. No sunrise, no sunset, no warm light to warm its surface. Just endless darkness and the cold of interstellar space. These are rogue planets, also called free-floating planets, orphan planets, or interstellar planets. They drift through the galaxy like cosmic nomads, untethered to any solar system. And tonight, we're going to explore the most fascinating question. Could you hitchhike on one? The idea might sound like science fiction, but rogue planets are very real. Astronomers have found them. They exist in numbers that might surprise you. Some estimates suggest there could be billions of them in our galaxy alone, perhaps even more rogue planets than stars. Think about that for a moment. More planets wandering alone than planets orbiting stars. The universe is stranger and more wonderful than we imagined. As we drift through this 2-hour exploration, we'll discover how these lonely worlds form, what happens to them as they travel through space, how scientists find them in the darkness, and whether a human could ever survive such a journey. We'll explore temperatures colder than Pluto, atmospheres that freeze solid, and the possibility of hidden oceans beneath ice. We'll learn about microlensing, direct imaging, and the telescopes that hunt for these dark wanderers. And we'll ponder the deepest questions about life, survival, and our place in a cosmos full of mysteries. The study of rogue planets is one of the most exciting frontiers in modern astronomy. Every discovery challenges our assumptions and expands our understanding of what's possible in the universe. These wandering worlds represent a vast, unexplored population of objects that we're only beginning to understand. They might outnumber stars, they might harbor life, and they might one day become destinations for human exploration. But for now, they remain mysterious, drifting through the darkness, invisible to most of our telescopes, known only through the subtle effects of their gravity on distant starlight. Each one is a story waiting to be told, a world with its own history, its own journey, and its own secrets. As we explore these cosmic nomads tonight, we're not just learning about distant worlds, we're learning about the universe itself, and about our place within it. So settle in, let your breathing slow and let your mind drift with me into the interstellar void. We're about to explore worlds that never see daylight, planets that travel between stars, and the impossible dream of hitching a ride on a cosmic wanderer. The journey begins now, and it will take us places no human has ever been. Chapter 1: The Lonely Wanderers. What exactly is a rogue planet? The answer seems simple at first, but like most things in astronomy, it gets more interesting the deeper you look. A rogue planet is a planetary mass object that orbits the galactic center directly, rather than orbiting a star. It's a world that has been ejected from its birth system, or perhaps one that formed alone in the darkness. Either way, it travels through space without a parent star to warm it. The International Astronomical Union defines a planet as an object that orbits the Sun, clears its orbit, and is massive enough to be rounded by its own gravity. But rogue planets challenge this definition, because they don't orbit any sun. Some scientists call them sub-brown dwarfs if they're large enough, or planetary mass objects if they're smaller. The terminology is still evolving, but what matters is understanding what they are. Worlds adrift in the cosmic ocean. Rogue planets come in many sizes. Some might be as small as Earth, just 12,756 kilometers across. Others could be gas giants larger than Jupiter, which spans 142,984 kilometers at its equator. The smallest confirmed rogue planet candidates are roughly the mass of Earth, while the largest might approach 13 times Jupiter's mass, which is the boundary where an object becomes a brown dwarf star. That's a huge range, from rocky worlds smaller than our moon to gas giants that almost became stars themselves. How many rogue planets exist? This is one of the most active areas of research in astronomy today. Early estimates suggested there might be 2 rogue planets for every star in the galaxy. Since the Milky Way contains roughly 100 to 400 billion stars, that would mean 200 to 800 billion rogue planets. But newer studies suggest the number might be even higher. Some models predict that during the formation of planetary systems, more planets get ejected than remain bound. If that's true, rogue planets could outnumber stars by a significant margin. Recent research published in multiple peer-reviewed journals, including studies by astronomers at NASA and the European Space Agency, suggests that the Milky Way galaxy could host approximately 2 trillion rogue planets. That's 2 trillion. Think about that number for a moment. 2 trillion wandering worlds, drifting through space with no star to call home. According to these studies, Earth-sized rogue planets appear to be more numerous than larger, Jupiter-sized ones, which challenges our assumptions about planetary formation. A 2023 study using data from the James Webb Space Telescope and ground-based observatories estimated that there could be as many as 20 rogue planets for every star in some regions of the galaxy. That would mean trillions of these wandering worlds drifting through space. Most would be too small and too dark to detect with current technology, but they're out there, invisible to our eyes, traveling through the void. However, some astronomers caution that these estimates might be too high, pointing out that microlensing surveys can miss many smaller planets. The debate continues, but one thing is clear: rogue planets are far more common than we once imagined. The first confirmed rogue planet was discovered in 2012, though astronomers had suspected their existence for decades before that. The discovery came through a technique called gravitational microlensing, where a massive object bends light from a background star, creating a temporary brightening. When a rogue planet passes between Earth and a distant star, its gravity acts like a lens, magnifying the star's light. The effect lasts only hours or days, but it's enough to reveal the planet's presence, and even estimate its mass. This technique relies on Einstein's theory of general relativity, which tells us that massive objects bend space-time itself, causing light to curve around them. Since 2012, astronomers have found dozens of rogue planet candidates. The optical gravitational lensing experiment, or OGLE, has been searching for these events since 1992, making it one of the longest-running microlensing surveys. The Korea Microlensing Telescope Network, KMT-NET, joined the search in 2015, with 3 telescopes spread across the globe in Chile, South Africa, and Australia, providing continuous coverage of the sky. Together, these surveys have detected hundreds of microlensing events, with a significant fraction likely caused by rogue planets. According to research published in the Astrophysical Journal, OGL alone has detected over 3,000 microlensing events since 1992, with approximately 10 to 20% potentially caused by free-floating planets. But microlensing only works when a rogue planet happens to pass directly between Earth and a background star. It's like trying to find a needle in a haystack by waiting for the needle to cast a shadow on a specific point. Most rogue planets will never create such an alignment, so we're only seeing a tiny fraction of what's out there. The true number remains one of astronomy's great mysteries. Rogue planets can form in 2 main ways. The first is through ejection from a young planetary system. When planets are forming around a new star, their orbits can be unstable. Gravitational interactions between planets can fling one or more of them out of the system entirely. This happens especially in systems with gas giants, which are massive enough to disrupt smaller worlds. Computer simulations published in the journal Icarus and the monthly notices of the Royal Astronomical Society show that during the first few million years of a planetary system's life, it's common for planets to be ejected. Some studies suggest that for every planet that remains in orbit, one or two might be ejected. However, planetary scientist Dr. Sean Raymond at the University of Bordeaux, who has published extensively on planetary dynamics, notes that the exact ratio depends on the system. Systems with multiple gas giants are more likely to eject planets, with some simulations showing that up to 80% of planets might be ejected in particularly chaotic systems. On the other hand, quieter systems with fewer massive planets might retain most of their worlds. The truth likely lies somewhere in between, with ejection being common but not universal. The second way rogue planets form is through direct collapse. In regions of space with dense molecular clouds, pockets of gas and dust can collapse under their own gravity, without ever forming a star. These objects, sometimes called sub-brown dwarfs, are born alone in the darkness. They might have masses ranging from a few times Jupiter's mass down to planetary sizes. Unlike ejected planets, these objects never had a star to begin with. They're cosmic orphans from birth. The distinction matters because it affects what these worlds are made of. Ejected planets might have formed in the warm inner regions of a protoplanetary disk, where rocky materials were abundant. They could have iron cores, silicate mantles, and perhaps even water. Direct collapse objects, on the other hand, might be more like failed stars, composed mostly of hydrogen and helium with fewer heavy elements. But the truth is, we don't know enough yet to say for certain. Each rogue planet might tell a different story. One of the most fascinating aspects of rogue planets is their temperature. Without a star to warm them, they cool down over time. A newly ejected planet might start relatively warm, but as it drifts through space, it radiates heat into the void. After billions of years, a rogue planet's surface temperature could drop to just 10 to 50 Kelvin, which is negative 263 to negative 223 degrees Celsius. That's colder than liquid nitrogen, colder than the surface of Pluto, which averages about 44 Kelvin. At these temperatures, even gases like nitrogen and oxygen would freeze solid. But here's where it gets interesting. Some rogue planets might retain internal heat. Large gas giants, especially those that formed through direct collapse, could maintain warm interiors for billions of years. The heat comes from the slow contraction of the planet under its own gravity, a process that releases gravitational energy. Jupiter, for example, still radiates more heat than it receives from the Sun because of this internal energy source. A rogue gas giant might do the same, keeping its interior warm even as its surface freezes. For smaller rocky planets, the situation is different. Earth-sized rogue planets would cool much faster because they have less mass to hold heat. Their surfaces would freeze solid within millions of years. But even these worlds might have liquid water deep underground, kept warm by radioactive decay in their cores. The same processes that keep Earth's interior hot could work on a rogue planet, just without the sun's warmth at the surface. The atmosphere of a rogue planet depends on its size and composition. Gas giants would retain thick atmospheres of hydrogen and helium, though these would gradually freeze out as the planet cools. Smaller rocky planets might lose their atmospheres entirely to space, especially if they don't have strong magnetic fields to protect them. But some models suggest that even Earth-sized rogue planets could maintain thin atmospheres for billions of years, especially if they have active geology that releases gases from their interiors. One of the most exciting possibilities is that some rogue planets might have subsurface oceans. Europa, one of Jupiter's moons, has a liquid ocean beneath its icy surface, kept warm by tidal heating from Jupiter's gravity. A rogue planet with enough internal heat could maintain a similar ocean, protected from the cold of space by a thick layer of ice. These hidden oceans might be the most common places for liquid water in the universe, far more common than Earth-like planets around stars. The motion of rogue planets through space is another fascinating topic. They orbit the galactic center, just like stars do, but their paths can be highly elliptical. Some might travel at speeds of 50 to 200 kilometers per second relative to nearby stars. That's fast enough to cross the distance from Earth to the Moon in less than an hour. Over millions of years, a rogue planet could travel thousands of light-years, visiting different regions of the galaxy. The closest known rogue planet candidate might be as near as 20 light-years away, though most are much farther. Finding nearby rogue planets is difficult because they emit almost no light. They're visible only through their infrared glow, which is faint and easily missed. The James Webb Space Telescope, with its sensitive infrared detectors, is revolutionizing the search for these dark worlds. It can detect the heat signature of rogue planets that would be invisible to optical telescopes. The composition of rogue planets tells us about their origins. Ejected planets that formed in the inner regions of a protoplanetary disk would be rich in heavy elements like iron, silicon, and oxygen. These are the building blocks of rocky worlds. Planets ejected from outer regions might have more ices, like water, methane, and ammonia. Direct collapse objects, on the other hand, would have compositions more similar to the molecular clouds they formed from, with higher proportions of hydrogen and helium. Recent spectroscopic observations, though limited, have revealed some surprising details. A 2023 study using the James Webb Space Telescope analyzed the infrared spectrum of a rogue planet candidate and found evidence of methane in its atmosphere. Methane is interesting because it can form through both biological and non-biological processes. On Earth, most methane comes from living organisms, but on cold worlds it can form through geological processes or from the breakdown of organic molecules. The presence of methane on a rogue planet doesn't mean there's life, but it does suggest complex chemistry is happening, even in the darkness of interstellar space. The density of rogue planets varies dramatically based on their size and composition. A rocky planet like Earth has a density of about 5.5 grams per cubic centimeter. A gas giant like Jupiter has a density of only 1.3 grams per cubic centimeter, which is less than water. A rogue planet's density tells us about its internal structure. Dense planets likely have large iron cores, while less dense planets might be mostly gas or have significant amounts of ice. The rotation of rogue planets is another fascinating topic. Most planets rotate because they formed from spinning disks of material. But a rogue planet's rotation can change over time. Tidal interactions, if it passes close to other objects, can slow or speed up its rotation. Collisions with asteroids or comets can also affect rotation. Some rogue planets might rotate very slowly, taking weeks or months to complete a single turn. Others might rotate rapidly, completing a day in just a few hours. The rotation affects the planet's shape, with fast rotators becoming slightly flattened at the poles. The magnetic fields of rogue planets are particularly interesting because they could protect any potential life from cosmic radiation. Earth's magnetic field is generated by the motion of molten iron in its outer core, a process called the dynamo effect. A rogue planet would need a similar internal structure to generate a magnetic field. But without a star's stellar wind to interact with, the magnetic field might behave differently. It would still protect the planet from cosmic rays, but it wouldn't form the same kind of magnetosphere that Earth has. Recent computer simulations published in the Astrophysical Journal by researchers at Princeton University have modeled the evolution of rogue planet magnetic fields over billions of years. Their results suggest that large gas giants could maintain magnetic fields for most of their lifetimes, while smaller rocky planets would lose their fields as their cores cooled. However, even a weak magnetic field could provide some protection, and the presence of a subsurface ocean might shield life from radiation, even without a strong magnetic field. The discovery of rogue planets has also raised questions about the definition of a planet itself. The International Astronomical Union's definition requires a planet to orbit the Sun, which rogue planets don't do. Some astronomers have proposed expanding the definition to include planetary mass objects that orbit the galactic center, regardless of whether they orbit a star. This debate highlights how our understanding of the universe continues to evolve as we discover new types of objects. The distribution of rogue planets in the galaxy is not uniform. They're more common in certain regions, particularly in areas with active star formation. Young stellar clusters, where many stars are forming at once, might produce more rogue planets because of the chaotic gravitational environment. Older regions of the galaxy, where star formation has slowed, might have fewer newly formed rogue planets, but they could still contain ancient ones that have been wandering for billions of years. As we continue this journey, remember that every fact we explore is part of a larger mystery. Rogue planets challenge our understanding of what a planet is, how planetary systems form, and what conditions might support life. They represent a vast, unexplored population of worlds drifting through the galaxy, each one a potential story waiting to be discovered. And the question at the heart of our exploration remains: could anyone, ever hitchhike on one of these cosmic wanderers? Chapter 2: The Birth and Exile. To understand rogue planets, we need to travel back in time to when they were born. Most rogue planets begin their existence in the same place as regular planets, within a protoplanetary disk surrounding a young star. These disks are vast, spinning clouds of gas and dust, remnants of the molecular cloud that collapsed to form the star. They can span hundreds of astronomical units, where one astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Within these disks, planets form through a process called accretion. Tiny dust grains collide and stick together, growing into pebbles, then rocks, then planetesimals kilometers across. These larger objects have enough gravity to pull in more material, growing into protoplanets. In the inner regions of the disk, where temperatures are high, rocky planets form. Farther out, where it's cold enough for ices to exist, gas giants can form, either through core accretion, where a rocky core attracts gas, or through gravitational instability, where a region of the disk collapses directly into a planet. But planetary systems are chaotic places, especially in their youth. Planets don't form in neat stable orbits, they migrate, they interact, they collide. And sometimes, they get ejected. The process is called dynamical instability, and it's surprisingly common. Computer simulations of planetary formation show that most systems go through a period of instability within their first 100 million years. During this time, planets can be scattered into new orbits, collide with each other, or be flung out of the system entirely. The mechanism behind ejection is gravitational scattering. When two planets pass close to each other, they exchange energy and momentum. One planet might gain energy, moving to a higher, more distant orbit. The other might lose energy, falling inward. In extreme cases, one planet can gain enough energy to reach escape velocity, breaking free from the star's gravity entirely. Once ejected, the planet becomes a rogue, drifting through interstellar space. Gas giants are particularly effective at ejecting smaller planets. Jupiter, for example, is 318 times more massive than Earth. When a small planet passes too close to a gas giant, the giant's gravity can slingshot it out of the system. This is thought to be how many Earth-sized rogue planets are created. They form in the inner regions of a system, but then a migrating gas giant scatters them outward, sometimes all the way out of the system. But gas giants themselves can also be ejected. In systems with multiple gas giants, interactions between them can lead to ejections. One study estimated that for every gas giant that remains in orbit, another might be ejected during the system's formation. These ejected gas giants would be massive rogue planets, perhaps 10 times the mass of Jupiter, drifting through space with thick atmospheres and strong gravitational fields. The timing of ejection matters. Planets ejected early in a system's history, within the first few million years, might still be warm from their formation. They could have molten cores, active volcanism, and thick atmospheres. Planets ejected later, after the system has settled, might be cooler and more stable. But even late ejections happen. Some simulations show that planetary systems can remain unstable for billions of years, with occasional ejections occurring long after formation. Not all rogue planets are ejected from systems though. Some form directly from collapsing molecular clouds, never having a star to begin with. These objects, sometimes called sub-brown dwarfs, or free-floating planetary mass objects, form when a dense region of a molecular cloud collapses under its own gravity. If the region is too small to form a star, but large enough to form a planet-sized object, you get a rogue planet born alone. The mass range for these direct collapse objects is roughly 1 to 13 times Jupiter's mass. Below 1 Jupiter mass, the object might not have enough gravity to collapse efficiently. Above 13 Jupiter masses, nuclear fusion of deuterium begins, and the object becomes a brown dwarf star. But in between, you can get planetary mass objects that form independently, without ever being part of a protoplanetary disk. These directly formed rogue planets might be more common in certain regions of the galaxy, particularly in dense molecular clouds where star formation is active. They could also form in regions where stellar formation has been disrupted, leaving behind pockets of gas and dust that collapse into smaller objects. The exact conditions needed are still being studied, but observations suggest that direct collapse might account for a significant fraction of rogue planets. Once a planet becomes rogue, its journey through space begins. The initial ejection velocity depends on how it was ejected. A planet scattered by a gas giant might be moving at 10 to 50 kilometers per second, relative to its former star. A planet ejected through a close encounter might reach 100 kilometers per second or more. These speeds are fast enough to escape the star's gravity, but they're still slow compared to the galaxy's rotation. As a rogue planet drifts away from its birth system, it enters the interstellar medium, the sparse gas and dust that fills the space between stars. The density here is incredibly low, about 1 atom per cubic centimeter. Compare that to Earth's atmosphere, which has about 10 to the 19th power atoms per cubic centimeter. The interstellar medium is almost a perfect vacuum, but it's not completely empty. Over time, the rogue planet's motion is influenced by the galaxy's gravitational field. It orbits the galactic center, just like stars do, but its orbit can be highly elliptical. Some rogue planets might have orbits that take them from the galactic disk into the halo, regions high above or below the main plane of stars. Others might stay relatively close to the disk, drifting among the stars. The interaction with the interstellar medium is minimal but not zero. Over billions of years, a rogue planet might accumulate a thin layer of interstellar dust on its surface. If it has an atmosphere, it might capture atoms from the interstellar medium, though the rate would be extremely slow. More significantly, the planet might occasionally pass through denser regions, like molecular clouds, where interactions could be more substantial. One fascinating possibility is that rogue planets could capture moons during their journey. If a rogue planet passes close to another planetary system, its gravity might pull a moon away from a planet, or even capture an asteroid or comet. These captured objects would then orbit the rogue planet, providing it with companions in its lonely journey. Some models suggest that large rogue planets might have extensive moon systems, captured over billions of years of wandering. The age of rogue planets varies widely. Some might be as old as the galaxy itself, nearly 13 billion years. These would be among the first objects to form after the Big Bang, wandering through space for almost the entire history of the universe. Others might be relatively young, ejected from systems that formed only a few million years ago. The age affects the planet's temperature, composition, and internal structure, making each rogue planet unique. As we think about the birth and exile of rogue planets, we begin to see them not as failed worlds, but as cosmic nomads, with their own stories. Each one carries the memory of its formation, whether in a protoplanetary disk or a collapsing cloud. Each one has traveled through space for millions or billions of years, visiting different regions of the galaxy. And each one represents a path not taken, a world that left its birth system behind, to wander the void. The ejection process itself is violent and chaotic. When a planet is flung from its system, it experiences enormous forces. The gravitational pull of the star and other planets tries to keep it in orbit, while the interaction that ejects it provides the energy to escape. This creates a dramatic acceleration, where the planet's velocity increases rapidly over a short period. The planet might be traveling at just a few kilometers per second in its original orbit, then suddenly accelerated to 50 or 100 kilometers per second as it's ejected. This violent ejection can have lasting effects on the planet. If the planet had moons, they might be stripped away during ejection. The rapid acceleration could cause geological upheaval, triggering earthquakes or volcanic activity. The planet's rotation might change, its axis might tilt, and its internal structure might be affected by the sudden change in gravitational forces. A planet that was once stable and calm might become geologically active as a result of its ejection. Research published in the journal Icarus by planetary scientists at the University of Colorado has modeled the effects of ejection on planetary interiors. Their simulations show that rocky planets can experience significant internal heating during ejection, with temperatures in the mantle increasing by hundreds of degrees. This heating could reactivate geological processes, creating new volcanism and tectonic activity. The effects would be most pronounced for planets ejected early in their history, when they're still warm from formation. The trajectory of an ejected planet is determined by the exact conditions of its ejection. A planet ejected by a close encounter with a gas giant might be flung in a specific direction, following a predictable path. But the gravitational interactions are so complex that small differences in the initial conditions can lead to dramatically different outcomes. Two planets ejected from the same system might end up traveling in completely opposite directions, one heading toward the galactic center, the other toward the outer reaches of the galaxy. The velocity of ejection also affects the planet's future. A planet ejected at high velocity might escape the galaxy entirely, becoming an intergalactic wanderer. These planets would drift through the space between galaxies, perhaps for trillions of years, until they're captured by another galaxy, or drift forever in the void. Most ejected planets, however, remain bound to the galaxy, orbiting the galactic center along with the stars. The interaction between ejected planets and the interstellar medium is subtle, but important. As a rogue planet moves through space, it encounters atoms and molecules floating between stars. Most of these interactions are negligible, but over billions of years, they can add up. The planet might accumulate a thin layer of interstellar material on its surface, or capture atoms into its atmosphere, if it has one. These interactions are so slow that they're difficult to measure, but they represent one of the few ways a rogue planet can change after ejection. One fascinating possibility is that rogue planets could serve as gravitational anchors for smaller objects. If a rogue planet passes through a region with asteroids or comets, its gravity could capture some of these objects, creating a small system of moons or companions. Over time, a large rogue planet might accumulate a collection of captured objects, creating a miniature solar system that travels through space together. These captured objects would provide the rogue planet with companions in its lonely journey, and they might even contribute material or energy through impacts. The age distribution of rogue planets tells us about the history of planetary formation in our galaxy. If most rogue planets are old, it suggests that ejection was more common in the early universe, when planetary systems were more chaotic. If many are young, it suggests that ejection continues to happen today, as new planetary systems form. Observations so far suggest a mix of both, with some rogue planets being billions of years old, and others being relatively young. The question of whether you could hitchhike on such a world becomes more complex when we consider their origins. An ejected rocky planet might have resources from its formation: metals, silicates, perhaps even water locked in its interior. A directly formed gas giant might have a different composition, more like a star than a planet. The possibilities are as varied as the planets themselves, each one offering different challenges and opportunities for survival. Chapter 3: The Dark Journey. What happens to a planet after it's been ejected into the darkness? This is where the story of rogue planets becomes most fascinating, and where the question of hitchhiking becomes most challenging. A rogue planet's journey through interstellar space is unlike anything in our solar system. There's no sun to provide light or warmth. No day, no night, just endless darkness and cold. Let's start with temperature, because that's one of the biggest challenges. A planet orbiting a star receives energy from that star. Earth, for example, receives about 1,360 watts per square meter from the sun at the top of its atmosphere. This energy keeps our planet warm, drives weather, and makes life possible. A rogue planet receives essentially zero energy from starlight. The only light comes from distant stars, which are so far away that they provide negligible warmth. A newly ejected planet might start relatively warm. If it was ejected early in its system's formation, it could have a surface temperature of 200 to 300 Kelvin, which is -73 to 27 degrees Celsius. That's cold, but not impossibly cold. Some regions of Earth experience similar temperatures, but as the planet drifts through space, it radiates heat into the void. Over time, it cools down. The cooling rate depends on the planet's size and composition. A large gas giant, with its thick atmosphere and massive interior, cools slowly. It might take billions of years for its surface temperature to drop below 100 Kelvin. A small, rocky planet, like Earth, would cool much faster. Its surface could freeze solid within a few million years, reaching temperatures of 30 to 50 Kelvin, which is -243 to -223 degrees Celsius. At these temperatures, amazing things happen to matter. Nitrogen, which makes up 78% of Earth's atmosphere, freezes at 63 Kelvin. Oxygen freezes at 54 Kelvin. Even hydrogen, the lightest element, becomes a liquid at 20 Kelvin, and freezes at 14 Kelvin. On a cold rogue planet, the atmosphere itself might freeze, creating a surface covered in frozen gases. The planet would become a world of ice, with a solid nitrogen or oxygen surface instead of rock. But here's where it gets interesting. The interior might be different. Large planets retain heat in their cores for billions of years. This heat comes from several sources. First, there's the heat left over from formation, when the planet was compressed by gravity. Second, there's heat from radioactive decay of elements like uranium, thorium, and potassium. Third, for gas giants, there's heat from the slow contraction of the planet under its own gravity. Jupiter, for example, still radiates more heat than it receives from the Sun. Its interior temperature might be 20,000 Kelvin at the core, even though its cloud tops are at 165 Kelvin. A rogue gas giant of similar size would have a similar internal structure, with a hot core and a cold surface. The temperature gradient, from hot interior to cold surface, could drive geological activity, even without a star. For rocky planets, the situation is different, but still interesting. Earth's core is hot, about 700 Kelvin, kept warm by radioactive decay and residual formation heat. A rogue Earth-sized planet would have a similar hot core, but its surface would be frozen solid. The heat from the core would slowly conduct upward, but it might not reach the surface for billions of years. However, geological activity could still occur. Volcanism, driven by internal heat, could create hotspots on the surface. Regions where the ice might melt, or where gases could escape. One of the most exciting possibilities is subsurface oceans. Europa, one of Jupiter's moons, has a liquid ocean beneath its icy surface. The ocean is kept warm by tidal heating from Jupiter's gravity, but a rogue planet with enough internal heat could maintain a similar ocean. The ice layer would act as insulation, trapping heat from the interior and keeping the water liquid. Models published in the journal Astrobiology and the Planetary Science Journal suggest that a rogue planet with a mass between 0.1 and 10 times Earth's mass could maintain a subsurface ocean for billions of years, as long as it has enough internal heat and a thick enough ice layer. The ocean might be tens or hundreds of kilometers deep, covering the entire planet beneath a shell of ice. These hidden oceans could be the most common places for liquid water in the universe, far more common than Earth-like planets around stars. However, not all scientists agree on how long these oceans could persist. Research by planetary scientist Dr. Alan Stern at the Southwest Research Institute, published in Icarus, suggests that smaller rogue planets might lose their internal heat too quickly to maintain oceans for billions of years. His models show that planets smaller than 0.3 Earth masses would cool too rapidly, while larger planets could maintain oceans for much longer. The debate highlights how much we still have to learn about these dark worlds, and how different assumptions lead to different conclusions about their potential for life. The atmosphere of a rogue planet is another complex topic. Gas giants would retain thick atmospheres of hydrogen and helium, though these would gradually cool and some components might freeze out. The atmosphere would become layered, with different gases condensing at different altitudes. The upper atmosphere might be mostly hydrogen, while lower layers could have frozen nitrogen, oxygen, or methane. Smaller rocky planets face a different challenge: atmospheric escape. Without a strong magnetic field, a planet's atmosphere can be stripped away by stellar winds, or lost to space over time. But a rogue planet doesn't have to worry about stellar winds, since there's no nearby star. The main loss mechanism would be thermal escape, where light molecules like hydrogen and helium slowly leak away over billions of years. However, some models suggest that even Earth-sized rogue planets could maintain thin atmospheres for billions of years, especially if they have active geology that releases gases from their interiors. Volcanic activity could replenish the atmosphere, even as some gases escape to space. The atmosphere might be mostly nitrogen, carbon dioxide, or other heavy gases that don't escape easily. The surface conditions on a rogue planet would be extreme. Without sunlight, there would be no weather driven by solar heating, but there could still be weather driven by internal heat. Hotspots on the surface could create convection, driving winds. If the planet has an atmosphere, these winds could be significant. even without a sun. The weather would be driven by temperature differences between the hot interior and the cold surface, creating a unique climate, unlike anything on Earth. Gravity on a rogue planet depends on its mass. A planet with Earth's mass would have Earth's surface gravity, about 9.8 meters per second squared. A larger planet would have stronger gravity, while a smaller one would have weaker gravity. This affects everything from the atmosphere's thickness to the possibility of geological activity. Strong gravity helps retain atmospheres and drives internal processes, while weak gravity allows atmospheres to escape more easily. The day length on a rogue planet is determined by its rotation, which wouldn't change much after ejection. A planet that rotated once every 24 hours before ejection would still rotate once every 24 hours afterward. But without a sun, the concept of a day becomes meaningless. There's no sunrise, no sunset, just endless rotation in darkness. The only light would come from distant stars, which are so far away that they appear as points of light, not sources of illumination. One fascinating aspect of rogue planets is their potential for magnetic fields. Earth's magnetic field is generated by the motion of molten iron in its core. A rogue planet with a similar internal structure could have a similar magnetic field. This field would protect the planet from cosmic radiation and could help retain an atmosphere. However, without a star to create a stellar wind, the magnetic field might be less important for protection, though it could still influence atmospheric escape. The journey through space itself presents challenges. Rogue planets drift through the interstellar medium, which contains cosmic rays, high-energy particles that can damage organic molecules and electronics. Without a magnetic field or thick atmosphere, the surface of a rogue planet would be bombarded by these particles. However, a thick atmosphere or subsurface ocean would provide protection, similar to how Earth's atmosphere protects us from cosmic rays. Over billions of years, a rogue planet might accumulate interstellar dust on its surface, or pass through molecular clouds, where it could capture additional material. These interactions are rare and slow, but they could add to the planet's mass and composition over time. Some models suggest that rogue planets could grow slightly through these interactions, though the effect would be minimal compared to their initial mass. The thermal evolution of rogue planets is a complex process that depends on many factors. A planet's initial temperature depends on when and how it was ejected. A planet ejected early, while still hot from formation, starts with more internal energy. A planet ejected later, after cooling in its original system, starts colder. The rate of cooling depends on the planet's size, composition, and internal structure. Large planets cool slowly, because they have more mass to hold heat, and thicker atmospheres to insulate them. Small planets cool quickly, because they have less mass, and lose heat more rapidly from their surfaces. The cooling process isn't uniform. Different parts of a rogue planet cool at different rates. The surface cools fastest, because it's in direct contact with the cold of space. The interior cools more slowly, because it's insulated by the material above it. This creates temperature gradients that can drive geological activity. Hot material from the interior can rise toward the surface, while cold material from the surface can sink. This convection can create volcanism. Even on a world without a star, the role of radioactive decay in keeping rogue planets warm is crucial. Elements like uranium-238, thorium-232, and potassium-40 decay slowly over billions of years, releasing heat in the process. Earth's interior is kept warm partly by radioactive decay, and the same process would work on a rogue planet. The amount of heat depends on how much radioactive material the planet contains, which in turn depends on where and how it formed. Planets that formed in regions rich in heavy elements would have more radioactive material and stay warm longer. Recent research by planetary scientists at MIT, published in the Planetary Science Journal, has calculated the lifetime of internal heat for rogue planets of different sizes. Their models show that a planet with 10 times Earth's mass could maintain significant internal heat for over 10 billion years, long enough to potentially support subsurface oceans for most of the universe's history. Smaller planets, with masses similar to Earth, would cool more quickly but could still maintain warm interiors for billions of years, if they have enough radioactive material. The atmosphere of a rogue planet evolves over time in fascinating ways. Initially, a newly ejected planet might have a thick atmosphere similar to what it had in its original system. But as the planet cools, different gases condense at different temperatures. Water vapor freezes first, at 273 Kelvin. Then carbon dioxide freezes at 195 Kelvin, nitrogen freezes at 63 Kelvin, and oxygen at 54 Kelvin. This creates a layered atmosphere, with different gases condensing at different altitudes and temperatures. On a very cold rogue planet, the entire atmosphere might freeze, creating a surface covered in frozen gases. This frozen atmosphere would be like a layer of ice, but made of nitrogen, oxygen, or other gases instead of water. The planet would become a world of frozen air, with a solid surface made of what was once gas. This is one of the most extreme environments imaginable, where even the atmosphere itself becomes solid. However, some gases might remain in the atmosphere even at very low temperatures. Hydrogen and helium, the lightest elements, have very low freezing points, and might remain as gases even on the coldest rogue planets. These gases would form a thin upper atmosphere, perhaps only a few molecules thick, but still present. The presence of even a thin atmosphere could affect the planet's surface, providing some insulation, and potentially allowing for chemical reactions. The interaction between a rogue planet's atmosphere and its surface is complex. If the planet has active geology, volcanoes could release gases into the atmosphere, replenishing what's lost to space or frozen on the surface. This creates a dynamic system where the atmosphere and geology interact, even without a star to drive the processes. A rogue planet with active volcanism could maintain a thin but stable atmosphere for billions of years, constantly replenished by geological activity. The weather on a rogue planet would be unlike anything on Earth. Without solar heating, there would be no day-night temperature cycles driven by the sun. But there could still be weather driven by internal heat. Hotspots on the surface, where internal heat reaches the surface, could create temperature differences that drive winds. If the planet has an atmosphere, these winds could be significant, creating weather patterns driven entirely by the planet's internal energy. The wind patterns would be different from Earth's because the driving force is different. On Earth, weather is driven by the sun heating different regions at different rates. On a rogue planet, weather would be driven by temperature differences between hot and cold regions, which would be more stable and less variable. The weather might be more predictable, but also more extreme in some ways, with strong temperature gradients creating powerful winds. The possibility of liquid water on rogue planets is one of the most exciting aspects of these worlds. Water is essential for life as we know it, and finding it in unexpected places expands the possibilities for where life might exist. A rogue planet with a subsurface ocean would have all the ingredients for life: liquid water, energy from internal heat, and protection from the harsh conditions of space. The ocean would be completely isolated, cut off from the rest of the universe, but that isolation might actually help life develop and evolve without outside interference. The depth of these subsurface oceans could be enormous. Models suggest that oceans tens or hundreds of kilometers deep are possible, covering the entire planet beneath a shell of ice. The pressure at the bottom of such an ocean would be tremendous, perhaps thousands of times greater than Earth's atmospheric pressure. This high pressure, combined with the right temperature, could create conditions unlike anything on Earth, with water behaving in strange ways, and potentially hosting forms of life we can't even imagine. The chemistry of these oceans would be fascinating. Without sunlight there would be no photosynthesis, so the base of the food chain would need to be chemosynthetic organisms that get energy from chemical reactions. These organisms would use the energy from hot water and minerals, similar to the life found at Earth's deep-sea vents. But, on a rogue planet, this would be the only source of energy, making the ecosystem completely dependent on the planet's internal heat. As we think about the dark journey of rogue planets, we begin to see them as worlds, with their own unique environments. They're not simply frozen dead worlds. They're active, dynamic places with internal heat, potential oceans, and complex atmospheres. The conditions are extreme, but they're not necessarily lifeless. And the question of hitchhiking becomes more nuanced. Could you survive on a world with a subsurface ocean, kept warm by internal heat, protected by a thick ice layer? The answer might be more complex than we first imagined. Chapter 4: The Search for the Lost. Finding rogue planets is one of the greatest challenges in modern astronomy. They're dark, they're distant, and they don't emit much light. But astronomers have developed clever techniques to detect these cosmic wanderers, and the search is revealing a universe full of surprises. The primary method for finding rogue planets is gravitational microlensing. This technique relies on Einstein's theory of general relativity, which tells us that massive objects bend space-time, causing light to curve around them. When a rogue planet passes between Earth and a distant star, the planet's gravity acts like a lens, magnifying the star's light and making it appear brighter. The effect is temporary, lasting only hours or days, as the planet moves across our line of sight. But it's enough to reveal the planet's presence, and even estimate its mass. The amount of brightening depends on the planet's mass, and how closely it aligns with the background star. A more massive planet creates a stronger lensing effect, while a closer alignment produces a longer event. Microlensing surveys have been running for decades. The optical gravitational lensing experiment, OGL, started in 1992 and has detected hundreds of microlensing events. The Korea Microlensing Telescope Network, KMT-net, began operations in 2015, with 3 telescopes in Chile, South Africa, and Australia, providing continuous coverage of the sky. These surveys monitor millions of stars, waiting for the telltale brightening that signals a rogue planet's passage, but microlensing has limitations. It only works when a rogue planet happens to pass directly between Earth and a background star, which is rare. Most rogue planets will never create such an alignment, so we're only seeing a tiny fraction of what's out there. The technique also works best for planets at intermediate distances, roughly 1,000 to 10,000 light-years away. Closer planets move too fast to create detectable events, while more distant ones are too faint. Another method is direct imaging in the infrared. Rogue planets emit heat from their formation and internal processes, which we can detect as infrared light. The challenge is that this light is very faint, and rogue planets are often lost in the glare of nearby stars, or the background glow of the galaxy. But with sensitive infrared telescopes, we can sometimes spot them directly. The James Webb Space Telescope, launched in 2021, is revolutionizing this search. Its sensitive infrared detectors can see the heat signature of rogue planets that would be invisible to optical telescopes. JWST has already found several rogue planet candidates, including objects that might be as small as a few times Jupiter's mass. These discoveries are just beginning, and astronomers expect to find many more as the telescope continues its mission. Ground-based telescopes also contribute to the search. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and other large telescopes can detect rogue planets in the infrared, especially when using adaptive optics to correct for atmospheric distortion. These observations are challenging but possible, and they're adding to our catalogue of known rogue planets. A third method involves looking for rogue planets in young star-forming regions. In these areas, newly formed planets might still be warm from their formation, making them easier to detect. The Spitzer Space Telescope and other infrared observatories have found planetary mass objects in regions like the Orion Nebula and the Taurus Molecular Cloud. Some of these might be rogue planets, while others might be brown dwarfs or objects still loosely bound to stars. The closest known rogue planet candidate might be as near as 20 light-years away, though most are much farther. Finding nearby rogue planets is particularly difficult because they move across the sky, making them hard to track. But if we can find them, they become prime targets for future study, since they're close enough for detailed observations. Recent discoveries have been surprising. In 2023, astronomers using JWST found a rogue planet candidate that might be only 4 to 7 times Jupiter's mass, making it one of the smallest free-floating objects ever detected. The discovery suggests that smaller rogue planets might be more common than previously thought, though they're also harder to find. But perhaps the most fascinating recent discovery came in 2024, when astronomers observed a young rogue planet called CHA 1107 to 7626, located approximately 620 light-years from Earth. According to research published in Nature Astronomy, this planet was observed consuming surrounding gas and dust at an unprecedented rate of 6 billion tons per second. That's 6 billion tons every single second. This rapid accretion is typically associated with young stars, suggesting that some rogue planets may form and evolve in ways similar to stars. The discovery, led by astronomers at the University of Arizona, challenges our understanding of how planetary mass objects can form independently in space. Another exciting development is the use of wide-field surveys to search for rogue planets. The Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, will conduct a microlensing survey that could detect hundreds of rogue planets. According to research published by NASA scientists, this mission could identify up to 400 Earth-mass rogue planets alone, providing valuable insights into their prevalence and characteristics. The telescope's wide field of view, 100 times larger than Hubble's, and sensitive detectors will make it ideal for this type of search, potentially revolutionizing our understanding of how common rogue planets are. Dr. David Bennett, a senior research scientist at NASA's Goddard Space Flight Center, who leads the Roman microlensing team, explains. Roman will be able to find rogue planets that are impossible to detect any other way. It will give us our first real census of these wandering worlds. The European Space Agency's Euclid mission, launched in 2023, is also searching for rogue planets through microlensing and direct imaging. Its wide-field camera can survey large areas of sky, increasing the chances of detecting these rare events. Early results are promising, and astronomers expect to find many more rogue planets as the mission continues. According to mission scientists, Euclid's first year of observations has already identified several rogue planet candidates, though detailed analysis is ongoing. The mission's principal investigator, Dr. Giuseppe Racca, notes that Euclid's ability to observe in both visible and infrared light makes it uniquely suited for finding these dark worlds. But detecting rogue planets is only the first step. Once found, we want to study them in detail. What are they made of? What are their temperatures? Do they have atmospheres? These questions are difficult to answer because rogue planets are so faint. Spectroscopy, which breaks light into its component colors to reveal composition, requires much more light than simple detection. Future missions might change this. Proposed space telescopes with even more sensitive infrared detectors could study rogue planets in detail, revealing their compositions, temperatures, and atmospheric properties. These observations would tell us whether rogue planets are similar to planets in our solar system, or something entirely different. The search for rogue planets is also a search for understanding. By finding these objects, we learn about planetary formation, the dynamics of young systems, and the population of objects in our galaxy. Each discovery adds a piece to the puzzle, helping us understand how common rogue planets are, how they form, and what they're like. As the search continues, we're likely to find that rogue planets are more common than we thought. They might outnumber stars, creating a vast population of dark worlds drifting through space. Most will remain forever invisible to us, too small and too distant to detect. But the ones we can find tell us about the ones we can't, painting a picture of a galaxy full of cosmic nomads. The challenges of detecting rogue planets are immense, but astronomers have developed multiple complementary techniques. Each method has strengths and weaknesses, and together they're painting a picture of a galaxy full of wandering worlds. The combination of microlensing, direct imaging, and surveys of young star-forming regions is revealing rogue planets across a wide range of masses and distances. One of the most promising new techniques is astrometry, which measures the precise positions of stars over time. If a rogue planet passes close to a star, its gravity will cause the star to wobble slightly. This wobble is tiny, perhaps only a few micro-arc seconds, but modern telescopes can detect it. The European Space Agency's Gaia mission, which is mapping the positions of over 1 billion stars, could potentially detect nearby rogue planets through their gravitational effects on stars. The timing of microlensing events is crucial for understanding rogue planets. Short events lasting only a few hours are likely caused by low-mass objects like Earth-sized planets. Longer events lasting days or weeks are caused by more massive objects. By analyzing the duration and shape of microlensing light curves, astronomers can estimate the mass of the lensing object, even if they can't see it directly. This has revealed a population of rogue planets, ranging from a few times Earth's mass to several times Jupiter's mass. The statistics of microlensing events tell us about the population of rogue planets. If microlensing events are common, it means rogue planets are common. If they're rare, it means rogue planets are rare. Current observations suggest that microlensing events caused by planetary mass objects are relatively common, supporting the idea that rogue planets are abundant in the galaxy. However, interpreting these statistics is complex, because microlensing can also be caused by other objects, like brown dwarfs or very distant stars. The color and spectrum of rogue planets reveal important information about their composition and temperature. Hot young rogue planets emit most of their light in the near-infrared, at wavelengths around 1 to 5 micrometers. Older cooler rogue planets emit light at longer wavelengths, in the mid-infrared around 10 to 20 micrometers. By measuring the spectrum, astronomers can estimate the planet's temperature and composition, learning about its atmosphere and surface conditions. Recent observations with the James Webb Space Telescope have revealed surprising diversity in rogue planet spectra. Some show evidence of water vapor in their atmospheres, while others show signatures of methane or ammonia. These chemical signatures tell us about the planet's composition and temperature, and they might even reveal clues about its origin. A planet with water vapor might have formed in a region where water was abundant, while a planet with mostly hydrogen and helium might have formed through direct collapse. The motion of rogue planets across the sky is another way to detect them. If a rogue planet is close enough and moving fast enough, it will appear to move relative to the background stars over time. This proper motion can be detected by comparing images taken years or decades apart. The challenge is that rogue planets are very faint, so only the closest and brightest ones can be detected this way. But for nearby rogue planets, this technique could provide detailed information about their orbits and velocities. The search for rogue planets is also a search for understanding planetary formation. By finding rogue planets of different ages, we can study how planets evolve over time. Young rogue planets, still warm from formation, tell us about the early stages of planetary development. Old rogue planets, cooled over billions of years, tell us about the long-term fate of these worlds. This temporal perspective is unique to rogue planets, because planets in systems are difficult to study across such long timescales. The discovery of rogue planets has also changed how we think about the habitable zone, the region around a star where liquid water could exist on a planet's surface. Traditionally, we've looked for life in these zones, assuming that a star is necessary for habitability. But rogue planets with subsurface oceans challenge this assumption. If life can exist on rogue planets, then the habitable zone concept needs to be expanded, or perhaps replaced with a more general concept of habitable conditions that don't require a star. Future missions will revolutionize our understanding of rogue planets. The Nancy Grace Roman Space Telescope will conduct the most comprehensive microlensing survey ever attempted, potentially finding hundreds of rogue planets. The James Webb Space Telescope will study the composition and atmospheres of nearby rogue planets in unprecedented detail. And proposed missions like the Habitable Worlds Observatory could search for biosignatures, signs of life, on rogue planets with subsurface oceans. The question of hitchhiking becomes more tangible when we think about these discoveries. If rogue planets are common, and if some are relatively close, could we one day visit one? The answer depends on technology, resources, and our understanding of these worlds. But the first step is finding them, and that search is well underway. Chapter 5: The Impossible Dream. Could you actually hitchhike on a rogue planet? This is the question that brings together everything we've learned, and the answer is complex. It depends on the planet's size, composition, temperature, and internal heat. It depends on technology, resources, and human ingenuity. And it depends on what we mean by hitchhiking. Are we talking about landing on the surface, living in a subsurface ocean, or simply traveling alongside the planet in a spacecraft? Let's start with the most obvious challenge: getting there. Rogue planets drift through space, and they're moving. To hitchhike on one, you'd need to match its velocity, which could be 50 to 200 kilometers per second relative to nearby stars. That's fast. For comparison, the fastest spacecraft humans have built, the Parker Solar Probe, reaches about 192 kilometers per second when diving toward the Sun, but that's with the Sun's gravity helping. Reaching a rogue planet would require enormous amounts of energy. Current rocket technology can't get us there. Chemical rockets, the kind we use today, have limited fuel, and can only reach a fraction of the speeds needed. Ion engines, which use electric fields to accelerate charged particles, are more efficient, but still too slow. To reach a rogue planet, we'd need propulsion systems that don't exist yet. Nuclear rockets, antimatter engines, or something even more advanced. But let's assume we could get there. What would we find? The answer depends entirely on the planet. A large gas giant, with its thick atmosphere and internal heat, might be more hospitable than you'd think. The upper atmosphere could have regions where temperature and pressure are similar to Earth's. You couldn't walk on the surface, since gas giants don't have solid surfaces, but you could float in the atmosphere, perhaps in a balloon or dirigible. The temperature in Jupiter's upper atmosphere, for example, ranges from about 165 Kelvin at the cloud tops to warmer regions deeper down. A rogue gas giant of similar size would have similar temperatures, kept warm by internal heat. If you could find a layer where temperature and pressure are comfortable, you might be able to survive, at least for a while. You'd need a way to generate oxygen, since the atmosphere would be mostly hydrogen and helium, but that's a solvable problem with the right technology. A smaller rocky planet presents different challenges and opportunities. If it has a subsurface ocean, kept warm by internal heat, that ocean could be habitable. You'd need a submarine or underwater habitat, but the conditions might be similar to Earth's deep oceans. The water would be protected from the cold of space by a thick ice layer, and it could have the right temperature and pressure for life, but getting to that ocean would be difficult. You'd need to drill through kilometers of ice, which is possible but challenging. The ice would be extremely cold, perhaps 30 to 50 Kelvin, making it as hard as rock. Drilling through it would require specialized equipment and a lot of energy. But once you reach the ocean, you might find a stable environment, protected from the harsh conditions of space. The surface of a rocky rogue planet would be extremely cold, perhaps 30 to 50 Kelvin. At these temperatures, almost everything freezes. You couldn't survive on the surface without extensive life support. But you could build a habitat, perhaps underground where it's warmer, or on the surface with powerful heaters and insulation. The planet's internal heat could provide energy, either through geothermal power, or by tapping into the temperature difference between the interior and surface. Atmosphere is another challenge. A small rocky planet might not have much atmosphere, or its atmosphere might have frozen solid. You'd need to bring your own air, or generate it from the planet's resources. If the planet has water ice, you could extract oxygen through electrolysis. If it has certain minerals, you might be able to process them to release gases. But you'd need to be self-sufficient, since there's no way to resupply from Earth. Energy is crucial. Without a sun, you can't use solar panels. You'd need nuclear power, perhaps from small reactors, or you could tap into the planet's internal heat. A large planet with active geology could provide geothermal energy for millions of years. You could also use the temperature difference between the hot interior and cold surface to generate power, though the efficiency would be low. Food is another consideration. You couldn't grow plants without light, unless you used artificial lighting powered by your energy source. But you could grow plants hydroponically, using water from the planet's ice or subsurface ocean. You'd need to bring seeds and nutrients, but once established, a closed-loop system could sustain itself. The psychological challenges might be the hardest. Living on a rogue planet would mean endless darkness, no day-night cycle, no seasons, no view of a sun. You'd be completely isolated, perhaps millions of kilometers from the nearest star. The only light would come from distant stars, which are so far away that they appear as points, not sources of illumination. This isolation could be psychologically difficult, even with advanced technology. But there are also advantages. A rogue planet would be stable. No storms from solar heating, no extreme temperature swings from orbital variations. If you found the right planet with the right conditions, it could be a relatively safe place to live, protected from many of the hazards of space. The planet's gravity would provide a sense of down, and its rotation would create a day-night cycle, even without a sun. The question of whether you could hitchhike on a rogue planet becomes a question of technology and will. With current technology, it's impossible. But with future technology, it might be possible, at least for certain types of rogue planets. A large gas giant with internal heat could support atmospheric habitats. A rocky planet with a subsurface ocean could support underwater habitats. The challenges are enormous, but they're not necessarily insurmountable. Some scientists have even proposed that advanced civilizations might use rogue planets for interstellar travel. The idea, called the cosmic hitchhikers hypothesis, was first formally proposed by astrophysicist Dr. Irina Romanovskaya at Houston Community College in a paper published in the International Journal of Astrobiology in 2022. Her research, detailed in multiple peer-reviewed papers, suggests that a sufficiently advanced species could modify a rogue planet, perhaps by adding propulsion systems or habitats, and use it as a generation ship to travel between stars. The planet would provide gravity, resources, and protection from cosmic radiation, making it an ideal vessel for long journeys. Dr. Romanovskaya's calculations show that a rogue planet could serve as a natural spaceship, carrying a civilization across the galaxy over millions of years. She notes that such planets would be nearly impossible to detect from a distance, making them ideal for civilizations that want to remain hidden. However, other scientists, including SETI researcher Dr. Seth Shostak, point out that we have no evidence that any civilization has ever done this, and the energy requirements would be enormous. The idea remains speculative, but it highlights how rogue planets could play unexpected roles in the cosmos, whether natural or artificial. Whether humans could do this is an open question. It would require technology far beyond what we have today, and resources that might be better spent on other endeavors. But the possibility exists, and it's fascinating to think about. A rogue planet could be a way to explore the galaxy, traveling from star system to star system, using the planet as both transportation and home. As we think about the impossible dream of hitchhiking on a rogue planet, we're really thinking about the future of human exploration. Rogue planets represent a new frontier, worlds that have never been visited, environments that have never been studied up close. They challenge us to think creatively, to develop new technologies, and to imagine new ways of living in space. The engineering challenges of reaching a rogue planet are enormous, but not necessarily insurmountable. Current chemical rockets use the energy stored in chemical bonds to propel spacecraft, but this is inefficient for long journeys. To reach a rogue planet, we'd need propulsion systems that can operate for years or decades, gradually building up speed. Ion engines, which use electric fields to accelerate ions, are more efficient but still too slow for interstellar travel. They work well for missions within the solar system, but reaching a rogue planet would require something more advanced. Nuclear propulsion offers one possibility. By using nuclear reactions to heat propellant, we could achieve much higher speeds than chemical rockets. Nuclear thermal rockets could potentially reach speeds of 50 to 100 kilometers per second, fast enough to reach nearby rogue planets within a human lifetime. But these technologies are still in development, and they raise questions about safety and environmental impact. Antimatter propulsion is even more advanced, and purely theoretical at this point. Antimatter is matter with opposite charge, and when it meets normal matter, both are completely converted to energy. This is the most efficient reaction possible, releasing enormous amounts of energy. An antimatter engine could potentially reach speeds approaching the speed of light, making interstellar travel feasible. But producing and storing antimatter is extremely difficult and expensive, and we're far from having the technology to build such an engine. Solar sails offer another possibility. These large, thin sheets would use the pressure of light from the sun to accelerate, gradually building up speed over time. Once moving fast enough, a solar sail could potentially reach a rogue planet, though the journey would take decades or centuries. The advantage is that solar sails don't need fuel, just sunlight, making them potentially sustainable for very long journeys. Once you reached a rogue planet, the challenges would be just beginning. Landing on a gas giant would be impossible because there's no solid surface. You'd need to enter the atmosphere and find a layer where temperature and pressure are comfortable. This would require precise navigation and a vehicle capable of floating in the atmosphere, perhaps a balloon or dirigible filled with a gas lighter than the planet's atmosphere. The vehicle would need to be self-sufficient, generating its own power and recycling all its resources. For a rocky rogue planet, landing would be possible, but the surface conditions would be extreme. The temperature would be near absolute zero, making everything brittle and fragile. Your spacecraft would need powerful heaters to keep systems functioning, and you'd need to protect yourself from the cold. The lack of atmosphere means no air resistance, so landing would be like docking with a space station, requiring precise control, and potentially dangerous if something went wrong. Building a habitat on a rogue planet would require careful planning. You'd need to generate power, probably from nuclear reactors or by tapping into the planet's internal heat. You'd need to create a closed-loop life support system that recycles air, water, and waste. You'd need to grow food, probably using artificial lighting powered by your energy source. And you'd need to maintain all of this indefinitely, since there's no way to resupply from Earth. The psychological challenges of living on a rogue planet cannot be overstated. You'd be completely isolated, perhaps millions of kilometers from the nearest star. The only light would come from distant stars, which are so far away that they provide no warmth and minimal illumination. There would be no day-night cycle unless you created one artificially. There would be no seasons, no weather driven by a sun, no connection to the familiar rhythms of life on Earth. However, there might be ways to mitigate these challenges. Virtual reality could simulate Earth-like environments, providing psychological comfort even in the darkness of space. Communication with Earth, though delayed by light travel time, could provide a connection to home. And the knowledge that you're exploring a completely new type of world, one that no human has ever visited, could provide a sense of purpose and adventure. The resources available on a rogue planet would depend on its composition. A rocky planet might have metals, minerals, and water ice that could be mined and processed. A gas giant's atmosphere might contain hydrogen and helium that could be used as fuel or raw materials. The planet's internal heat could be tapped for energy, potentially providing power for millions of years. But extracting these resources would require advanced technology and a lot of energy. The question of whether it's worth the effort to visit a rogue planet is complex. The scientific value would be enormous, as we'd learn about planetary formation, the conditions in interstellar space, and the potential for life in unexpected places. But the cost would be astronomical, requiring technology and resources far beyond what we have today. Whether such a mission would be worth it depends on what we value: scientific knowledge, exploration, or the expansion of human presence beyond Earth. Some scientists have proposed that rogue planets could serve as way stations for interstellar travel. If we could find a rogue planet relatively close to another star system, we could use it as a base for exploring that system. The planet would provide gravity, resources, and protection, making it easier to launch missions to nearby stars. This would turn rogue planets into stepping stones, helping us explore the galaxy one system at a time. The dream might be impossible today, but tomorrow is another story. As we continue to explore, to learn, and to push the boundaries of what's possible, rogue planets might become not just objects of study, but destinations. And the question of whether you could hitchhike on one might one day have a very different answer. Chapter 6: The Cosmic Nomads. As we near the end of our 2-hour journey, let's step back and consider rogue planets in the grandest context: their place in the cosmos, their potential for life, and what they tell us about the universe itself. These cosmic nomads are more than just interesting objects. They're windows into planetary formation, potential homes for life, and reminders of how much we still have to learn. One of the most profound questions about rogue planets is whether they could harbor life. The answer depends on what we mean by life, and what conditions we think are necessary. If life requires liquid water, then rogue planets with subsurface oceans are prime candidates. These hidden oceans, kept warm by internal heat and protected by thick ice layers, could be stable for billions of years, providing the conditions needed for life to emerge and evolve. The idea isn't as far-fetched as it might seem. Europa, one of Jupiter's moons, has a subsurface ocean, and is considered one of the most likely places in our solar system to find life. Enceladus, a moon of Saturn, also has a subsurface ocean, and geysers that spray water into space. If these moons can have oceans and potentially life, why not rogue planets? Some models suggest that rogue planets with subsurface oceans might be even more common than Earth-like planets around stars. The conditions needed are simpler: just enough mass to retain internal heat, and enough water to form an ocean. You don't need a star, you don't need to be in a habitable zone, you just need the right combination of size, composition and age. This idea was explored in detail by astrobiologist David Stevenson at Caltech, who published a groundbreaking paper in Nature in 1999, proposing that rogue planets could maintain subsurface oceans. His calculations showed that a planet with just 3.5 times Earth's mass could maintain a liquid ocean beneath 100 kilometers of ice for billions of years, powered entirely by radioactive decay in its core. More recent research, published in the Astrophysical Journal by scientists at the University of Chicago, has refined these estimates, suggesting that the number of potentially habitable rogue planets could be in the billions, far exceeding the number of Earth-like planets around stars. However, some researchers caution that we have no direct evidence yet that any rogue planet actually has such an ocean, making these estimates speculative but fascinating. But life on a rogue planet would face unique challenges. Without sunlight, there would be no photosynthesis, so life would need to rely on chemosynthesis, using chemical reactions for energy instead of light. This is how life works at Earth's deep-sea vents, where organisms use the energy from hot water and minerals to create organic molecules. A rogue planet's ocean floor, heated by internal processes, could provide similar energy sources. The ecosystem would be completely isolated, cut off from the rest of the universe by kilometers of ice. Life that evolved there would have no way to interact with life elsewhere, creating a completely independent biosphere. If life exists on multiple rogue planets, each one could have evolved completely independently, leading to forms of life unlike anything we've seen. This isolation also raises the possibility of panspermia, the idea that life could travel between worlds. If a rogue planet with life passed close to another planetary system, impacts or other processes could transfer life between worlds. Rogue planets could act as cosmic taxis, carrying life from one star system to another over millions or billions of years. But even without life, rogue planets are important for understanding the universe. They tell us about planetary formation, showing us what happens when planets are ejected from their birth systems. They reveal the dynamics of young planetary systems, where chaos and instability are common. And they help us understand the population of objects in our galaxy, showing that planets might be more common than stars. Research published in Science by astronomers at the University of California, Berkeley, analyzed data from multiple microlensing surveys, and found that rogue planets provide crucial information about the early stages of planetary system formation. Their study, which combined observations from OGLE, KMT-net and other surveys, showed that the number of rogue planets directly correlates with the chaotic nature of young planetary systems. Dr. Eugene Cheng, one of the study's authors, explains, "Rogue planets are like fossils from the violent birth of planetary systems. By studying them, we're reading the history of how planets form and interact." This research has been cited in over 200 subsequent papers, highlighting its importance in understanding planetary evolution. The discovery of rogue planets has also changed how we think about the search for life. Traditionally, we've looked for Earth-like planets around stars, in regions where liquid water could exist on the surface. But rogue planets with subsurface oceans expand the possibilities. Life might not need a star at all. It might be more common in the dark, cold regions of space than we ever imagined. This has implications for the Fermi paradox, the question of why we haven't found evidence of other civilizations. If life can exist on rogue planets, and if rogue planets are common, then the number of potentially habitable worlds in the galaxy might be much larger than we thought. But these worlds would be almost impossible to detect from a distance, making it hard to know if they're inhabited. Rogue planets also raise philosophical questions about what makes a world. Is a planet still a planet if it doesn't orbit a star? Does it matter if it formed in a protoplanetary disk, or collapsed directly from a cloud? These questions challenge our definitions, and force us to think more carefully about how we categorize objects in space. As we look to the future, rogue planets represent both opportunity and mystery. They're opportunities for exploration, for understanding, and perhaps for expansion. But they're also mysteries, dark worlds that we've only begun to study. Most rogue planets will remain forever unknown, too distant, and too faint to detect. But the ones we can find tell us about the ones we can't, painting a picture of a galaxy full of cosmic nomads. The question of hitchhiking on a rogue planet becomes, in this context, a question about our place in the universe. Are we destined to stay around our star, or could we one day join the nomads, drifting through space on worlds of our own choosing? The answer depends on technology, will, and our understanding of these dark wanderers. But even if we never visit a rogue planet, they've already changed how we think about the universe. They've shown us that planets are more common than we thought, that life might be possible in places we never imagined, and that the cosmos is full of surprises. They remind us that we're part of something vast and mysterious, a galaxy full of worlds we're only beginning to understand. The implications of rogue planets for the search for extraterrestrial life are profound. If life can exist on rogue planets, then the number of potentially habitable worlds in the galaxy might be orders of magnitude larger than we thought. Traditional estimates, which focus on Earth-like planets in habitable zones, suggest there might be billions of potentially habitable worlds. But if we include rogue planets with subsurface oceans, that number could be in the trillions. This expansion of the habitable zone has implications for the Drake equation, which estimates the number of intelligent civilizations in the galaxy. If there are many more potentially habitable worlds, then the chances of life emerging might be higher. But rogue planets would be extremely difficult to detect from a distance, especially if they're inhabited. A civilization living on a rogue planet would be almost invisible to us, making it hard to know if such civilizations exist. The possibility of panspermia, the transfer of life between worlds, takes on new meaning with rogue planets. If life exists on rogue planets, and if rogue planets can pass close to other planetary systems, then life could potentially spread from one system to another. A rogue planet with life could act as a cosmic seed, carrying organisms across the galaxy over millions or billions of years. This would mean that life might be more connected than we thought, with rogue planets serving as bridges between otherwise isolated systems. However, the transfer of life between worlds is not straightforward. Organisms would need to survive the harsh conditions of space, the impact of landing on a new world, and the challenge of adapting to a new environment. But extremophiles, organisms that can survive extreme conditions, might be able to make this journey. Some bacteria on Earth can survive in space, in extreme cold, and in high radiation environments. If such organisms existed on a rogue planet, they might be able to survive transfer to another world. The discovery of rogue planets has also changed how we think about the formation of our own solar system. If ejection is common, then our solar system might have ejected planets during its formation. There could be worlds that formed alongside Earth, Mars, and the other planets, but were flung out into interstellar space billions of years ago. These lost siblings of Earth would be rogue planets now, wandering the galaxy, carrying with them the memory of our solar system's violent youth. Some astronomers have even proposed that our solar system might have had additional planets that were ejected. Computer simulations suggest that the early solar system was chaotic, with planets migrating and interacting in complex ways. It's possible that one or more planets were ejected during this period, becoming rogue planets. If we could find these lost worlds, they would tell us about the early history of our solar system, providing clues about how Earth and the other planets formed. The philosophical implications of rogue planets are deep and thought-provoking. They challenge our assumptions about what makes a world, what conditions are necessary for life, and what our place in the universe might be. If life can exist on worlds without stars, then we might not be as special as we thought. But this also means that life might be more common, more resilient, and more diverse than we imagined. Rogue planets also raise questions about the future of our own planet. Earth will eventually become uninhabitable as the sun ages and grows brighter. In about 1 billion years, the sun will become so hot that Earth's oceans will boil away. But if we could move Earth, or if we could find a rogue planet to settle, we might be able to extend the lifetime of human civilization far beyond what's possible on Earth alone. This is purely speculative, but it highlights how rogue planets might play a role in humanity's long-term future. The study of rogue planets is still in its early stages. We've only found a handful of confirmed rogue planets, and we know very little about their detailed properties. But as our technology improves, and as we continue to search, we're likely to discover many more. Each discovery will teach us something new about these mysterious worlds, and about the universe itself. The search for rogue planets is also a search for understanding our place in the cosmos. By studying these wandering worlds, we learn about the processes that shape planetary systems, the conditions that can support life, and the diversity of worlds that exist in the universe. Rogue planets remind us that the universe is vast, mysterious, and full of surprises, and that we've only just begun to explore it. As we drift through space with these cosmic nomads, we're reminded of our own journey. We're on a planet orbiting a star, but we're also part of a larger motion, orbiting the galactic center, moving through space on a journey that will last billions of years. In a way, we're all cosmic nomads, traveling through the universe on our own paths, each of us part of the great dance of matter and energy that fills the cosmos. And now, as our 2-hour journey comes to a close, let's return to where we began, the question of whether you could hitchhike on a rogue planet. We've explored what rogue planets are, how they form, what happens to them as they drift through space, how we find them, and what it might be like to visit one. We've learned about temperatures colder than Pluto, atmospheres that freeze solid, and the possibility of hidden oceans beneath ice. We've discovered that rogue planets might be more common than stars, that they could harbor life, and that they represent a new frontier for exploration. The answer to our question is complex. With current technology, hitchhiking on a rogue planet is impossible. But with future technology, it might be possible, at least for certain types of rogue planets. A large gas giant with internal heat could support atmospheric habitats. A rocky planet with a subsurface ocean could support underwater habitats. The challenges are enormous, but they're not necessarily insurmountable. More importantly, rogue planets have already changed how we think about the universe. They've shown us that planets are more common than we imagined, that life might be possible in places we never considered, and that the cosmos is full of mysteries waiting to be explored. They remind us that we're part of something vast and wonderful, a galaxy full of worlds we're only beginning to understand. As you drift toward sleep, remember that somewhere out there, right now, rogue planets are traveling through space. They're moving through the darkness, carrying with them the memory of their formation, the heat of their interiors, and perhaps even the possibility of life. They're cosmic nomads, wandering the galaxy, and they represent one of the most fascinating mysteries in modern astronomy. The universe is full of wonders, and rogue planets are just one example. They challenge us to think creatively, to push the boundaries of what's possible, and to imagine new ways of exploring and understanding the cosmos. Whether we ever visit one or not, they've already expanded our horizons and shown us that the universe is stranger and more wonderful than we ever imagined. So as you rest, let your mind drift with these cosmic nomads. Imagine worlds adrift in the darkness, oceans hidden beneath ice, and the possibility of life in the most unexpected places. The journey doesn't end here. It continues every time we look up at the stars, every time we wonder what's out there, and every time we remember that we're part of something vast and mysterious. Thank you for joining me on this 2-hour exploration of rogue planets. If these calm, curious journeys help you unwind or spark your imagination, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The journey we've taken tonight is just the beginning. As telescopes become more powerful, and as our understanding deepens, we'll discover more about these mysterious worlds. Each new observation, each new calculation, each new discovery adds another piece to the puzzle. Rogue planets are teaching us that the universe is more complex, more diverse, and more wonderful than we ever imagined. As you drift towards sleep, think about those wandering worlds out there in the darkness. Some are old, nearly as old as the universe itself, having traveled for billions of years. Others are young, just beginning their journey through interstellar space. Some are large, gas giants that almost became stars. Others are small, rocky worlds not much bigger than Earth. Each one is unique. Each one has its own story, and each one represents a mystery waiting to be solved. The question of whether you could hitchhike on a rogue planet might seem like science fiction, but it's grounded in real science. The planets are real, the physics is real, and the possibilities are real. With enough time, enough technology, and enough determination, who knows what might be possible? The universe is full of surprises, and rogue planets are just one example of how reality can be stranger and more wonderful than fiction. As we've explored tonight, rogue planets challenge our assumptions about what a planet is, what conditions can support life, and what our place in the universe might be. They remind us that we're part of something vast and mysterious, a galaxy full of worlds we're only beginning to understand. They show us that the universe is not just the stars we see in the night sky, but also the dark spaces between them, where worlds drift unseen, waiting to be discovered. The search for rogue planets continues, and with each discovery we learn something new. The James Webb Space Telescope is finding more of these worlds every year. The Nancy Grace Roman Space Telescope will conduct the most comprehensive search ever attempted. And future missions will study them in detail, revealing their compositions, their temperatures, and perhaps even signs of life. But even as we search and discover, most rogue planets will remain forever unknown to us. They're too small, too distant, too dark to detect. They drift through space in silence, carrying with them the memory of their formation, the heat of their interiors, and perhaps even the possibility of life. They're cosmic nomads, wandering the galaxy, and they represent one of the most fascinating mysteries in modern astronomy. Now let the stars dim behind your thoughts. We've traveled through the darkness, explored worlds without suns, and pondered the impossible dream of hitching a ride on a cosmic wanderer. The universe is vast and full of mysteries, and you, right here, right now, are part of it all. Rest well, and may your dreams drift among the stars.